My name is Mark Verloosdrecht. I work at Delft University of Technology in the Department of Biotechnology, and I work mainly on the study of microorganisms and how we can apply them in novel and innovative processes around wastewater treatment. This lecture is about one of the features of activated sludge, the sludge itself. There have been other lectures on the activated sludge process and the settling of bacteria in the final clarifier. This lecture will mainly focus on the sludge volume index, or what determines the sludge volume index, and especially why sometimes filamentous organisms are growing in the sludge, causing so-called bulking sludge. The bulking sludge is one of the most significant problems for activated sludge treatment plants. It on one hand leads to a very bad settling sludge. On the other hand, part of the filamentous organisms also attach very well to gas bubbles and cause then foaming on top of the treatment plant when you aerate the plant. The lecture is the overall chapter is divided in 4 lectures. First, a general introduction, that is this lecture, then a lecture on some laboratory study on what causes filamentous organisms to grow, and then a lecture on practical implications, and finally a lecture on microscopic evaluation of activated sludge, which will be given by Per Nielsen. What is bulking sludge? Bulking sludge is the presence of excessive quantities of filamentous organisms that either expand the activated sludge floc, resulting in a lower density. You get a lot of water in between and then the overall density decreases. And these filaments can extend beyond the floc particles and physically hold them apart in the bulk solution. On the picture you see an example of a filamentous organism, long thread-like organisms, and you can imagine that will settle much more difficult than a compact floc structure or even a granule. Here you see again an electron microscopic picture of such filamentous organisms, showing their thread-like structure and their open and porous character, leading to the low density of the sludge. Now, bulking sludge is a long-lasting problem. Actually, as long as the wastewater treatment plant is applied and that's for more than a century, it's a long-lasting problem. Each time it comes back. Why is this? It's a complex interaction between biology and engineering. It's not simply a biological problem, it's not simply an engineering problem, it's the interaction between these two. And over time it has always been difficult to communicate between different disciplines the really relevant aspects of that interaction between microbes and their physical environment. On top of that, there's in the practice a lot of empirical or anecdotal information, which is usually based on good observations, but the interpretations are not always correct and they start to live their own life, complicating the discussions. The bulking sludge itself is a process engineering problem. It results from wrong design of the treatment plant essentially. But it's a microbial phenomena, so the tendency is to try to look to the microbiology, but you have to look to the microbiology, and that can tell you what is wrong in the process engineering and then adapt the process engineering aspects of the plant if possible. Now, over time, bulking sludge has been very well studied, and many factors are of influence. I'm not going to go through this slide in detail. It's just showing what is all present in literature as aspects which influence the sludge settleability and the growth of filamentous organisms. And that is summarized in the review article which is on this slide. Now, the bulking sludge is especially from importance because it increases the sludge volume index. And the higher the sludge volume index, that is the volume of 1 gram of sludge after settling, the larger that sludge volume index, the larger the clarifier has to be. And if you look to an average wastewater treatment plant, then you see that in general the clarifiers occupy roughly half of the treatment plant. Now, if you can decrease the sludge volume index, then of course you can make the settlers smaller. But if the sludge increases in sludge volume index after you have designed the clarifier, then the clarifier is effectively too small and the sludge will float out of the clarifier into the effluent, deteriorating the effluent quality. Now, the functions of sludge settling is clarification and thickening. The first part is just the settling of the sludge. The second part is the thickening of the sludge. Now, both are affected because you can imagine that if you have a flock, this filamentous organism is also on the right hand side picture. This flock will have a lower settling velocity than when these filaments are not present. Moreover, when the flocks are packed, these filaments will keep the flocks apart and the thickening or compression of the sludge into a compact, high concentration will not occur. Now, the sludge settability is determined by the sludge volume index. That's a characterization number, and the sludge volume index we express in the milliliters of volume 1 gram of settled sludge occupies. And we do that by taking a 1 or 2 liter cylinder, put in the activated sludge mixture in that cylinder, let it settle for 30 minutes and measure the volume after 30 minutes. Now, that volume after times 1000 to go from liters to milliliters, divided by the MLSS in gram per liter is the sludge volume index. With the volume as, one aspect is that if you have bulking sludge and the sludge volume index becomes too large, you cannot really measure it. Then you have to use a diluted sludge volume index, and it is advised that if you start with 1 liter of activated sludge mixture, that the settled volume is smaller than 250 milliliters to have a representative measure of the accurate measure of the sludge volume index. Why is the sludge volume index important? Well, that's more or less, there is, at least for a range of sludge volume index, a direct correlation between the sludge volume index of a sludge and the required area of a clarifier, the settler. And you see on the left hand side a well settling sludge, on the right hand side in the picture a not so well settling sludge. And you see that if you go from a sludge volume index from 100 to 150, you more or less have a doubling of the area of the clarifier you need to construct. So striving for a good settleability, a low sludge volume index, so a low amount of filamentous organisms, reduces the land area requirement. You can also have a better process control, and it increases the plant performance overall, also due to lower settled suspended solids in the effluent. Now, bulking sludge occurs each time, several times in the development of wastewater treatment processes. The original process in 1914 for general wastewater treatment and in 1950 for nitrogen removal, they were fill and draw reactors, or sequencing batch reactors as we call them. They fill at a certain moment. You have a react phase, a settle phase, a draw phase, wastage and an idle time. In this case, the sludge gets loaded with high organic carbon at the start of the cycle, and during the cycle the carbon disappears from the water and you end up with clean water. Such a sequencing batch reactor is a more complex operation than a continuous operation. So after the in the case of Arden Locker, but also in the case of Pasveer, engineers wanted to go to more continuous operation instead of this fill and draw reactors. But then you change the behavior, because then you have an aeration tank, and instead that you have a high dose of organic carbon to the sludge, you have a continuous dose of organic carbon to the sludge, leading to a continuous low concentration of COD in the aeration tank, and that is directly associated with the settling problems. This transition from the fill and draw reactor from Arden Locker to the continuous operation plants was maybe engineering easier to do, but it gave then the complexity of the microbiology and the risk of bad settling. The same for the nutrient removal. Donaldson-Davidson and also Pasveer made sequencing batch reactor or a plug flow. And essentially a plug flow reactor is, from the observation of the microorganisms, more or less the same, because at the start of the plug flow to get a high substrate concentration. During the travel through the plug flow, the substrate is consumed and you have a kind of what you call famine phase. And also the operations where you have a clear separation in redox zones, pure anoxic, no oxygen intrusion, pure aerobic, are good for nitrification, denitrification. But again, they are more complex to build, and designers rather move to step feeding and the oxidation ditch, not as a sequencing batch reactor, but again as a continuous process. And again, these continuous processes, the step feed processes, easily lead to increase in the sludge volume index, partly again because something with the loading of the flux with organic carbon, with the COD, partly because the redox zones are not clearly differentiated from each other anymore. You have parts where there is some aeration and slowly oxygen is moving out. Now, if you look to the bulking sludge microbiology, there's a lot of studies in the literature. Until, say, 10-15 years ago, they were mainly based on microscopy. That's what Per Nielsen also later will tell you more about. Nowadays, they are much more based on DNA analysis of the sludge and giving a more direct, concrete name. However, observing how the sludge flux look like, certainly with bulking sludge, gives a lot of information on the behavior of the plant. There are many different organisms described. They are all associated with some causative conditions which lead to that, like a pH that is off, low DO, low loading of the flux, very long sludge ages, slowly biodegradable or particulate substrates. There are many there, but the point is that if you look in that literature, there are no good certainties about the causative conditions. They're all indications to try to make a link. As I said, the study of the bulking sludge microbiology, there's a good manual, and it's still available online on the website where it's there, which gives you a good manual for microscopic observation of activated sludge microbiology and filamentous organisms in specific. And nowadays there's a good DNA database, the MIDAS field guide, which can help to analyze metagenome data to analyze which filamentous bacteria are present. And both, I advise you to visit these websites if you want to know more. Now, the basic theory behind why filamentous organisms will win the competition of floc formers. And wastewater treatment, if we get different organisms, we always have to think, why will this organism win the competition over the other organisms? Now, this basic so-called kinetic selection theory was formulated by Chudoba somewhere in 1973. And that selection theory states that the filaments have a high affinity and a low growth rate compared to floc formers. What you see in this graph is the substrate concentration on the x-axis and the substrate uptake rate on the y-axis. The red line is for the filaments, the blue line is for the floc formers, and the formula in the bottom is describing these lines. And in the formula you see a QS max, that is in the end the maximum rate, more on the right hand side of the graph, and the KS is the substrate concentration at which the organisms reach half of the maximum rate. Now, what you see is that at the low substrate concentration, the red organism, the filamentous organisms, take up the substrate faster than the blue organism, meaning that the filamentous organism win the competition from the blue organisms, whereas at high substrate concentration, the blue organisms win the competition. This is reflected from the observations from practice, where you see that if you have a high oxygen concentration or a high loading rate, so you have a high concentration of COD in the reactor initially, and later a zero concentration, then the flock formers will win. If you have a low oxygen concentration, or you have a completely mixed reactor, meaning your substrate concentration in the reactor is always very low, the red or the filamentous organisms will win. This kinetic selection theory can pretty well help in analyzing and understanding why you get bulking sludge, although it might not be 100% correct. Around the same time, in 1974, Rensink proposed to add a selector tank to installations that show bulking. In this case, an oxidation ditch is then upgraded by adding a small plug flow reactor in front of the oxidation ditch, where the waste activated sludge is mixed with the incoming influent. These so-called selectors simulate what you have in a sequencing batch reactor or in a plug flow reactor. Initially the flocks see a high COD concentration, and they then can take it up, and the flock forming organisms can win the competition from the filamentous organisms. And when then the sludge goes into the oxidation ditch itself, then most of the easy degradable BUD is removed, and you do not have much chance for filamentous organisms to grow. And these are the original data from Rensink's paper. On the left-hand side is the system without a selector. You have a sludge volume index of 200 to 250 milliliter per gram, or milligram per liter, I mean. On the right-hand side, you see that certainly in the summer months, all of the year, the sludge volume index is below 150 milliliters per gram, which is the design criteria of the clarifiers. Moreover, in summer you even go down to around 100, which means that in summer you could even deal with a smaller clarifier. Now, after that, a whole range of selector designs appeared, a lot of different variations. They are summarized in this table. Again, I'm not going to go through the table in detail. You can read it in the review paper, which is on the right bottom side of the paper. These guidelines, they vary a bit from place to place. You see also the authors have different opinions. We will come back at the end of this lecture series. I will come back at the third lecture on the more practical aspects of this. There are several theories in the literature besides the kinetic selection theory that try to explain why filamentous organisms could win the competition of flock forming organisms. The first one, which is has been quite around, is that filamentous bacteria have a lower capacity for substrate storage. This is not correct. Virtually all filamentous organisms can, like the flock formers, take up COD, store it inside the cell, preserve it for the later phase in the process when there's no external COD anymore, but enough oxygen, and then grow on it. So this theory is clearly not correct. Then there are two other theories. One, that the filamentous organisms have a different maintenance, have lower maintenance requirements. That's why at longer SRTs you seem to easier find filamentous organisms, but usually longer SRTs means also lower flock loading rates. And inhibition by denitrification intermediates. If you have denitrification, you might have NO or N2O accumulating, and they might influence the competition between the flock formers and the filamentous organisms. For both theories, they are around in literature, but there is no solid evidence that one of them is right. Now, the bulking sludge study itself, as mentioned in the start already, there's a lot of anecdotal information from installations where bulking sludge occurs. People do something, it helps, but don't measure all the data, and that leads to a hearsay type of information where you always have to be a bit critical on what was really happening at the treatment plant of observation. The recognition of bacteria was mainly based on the morphology. This is difficult because, of course, you can much better see filamentous bacteria different morphologies than flock-forming bacteria because they're all more or less coccoidal. Filamentous bacteria might be branched, might have different structures, so there is a better recognition, but it's still not based on physiological properties. And the only way to study that better is in a lab scale system, in a proper scale down system. And that will be in the second lecture of this chapter. With that, I want to finalize this lecture and see you back at the second chapter of this lecture.